Hello and welcome back to this lecture series on aluminum based alloys and metal matrix composites.
Okay, so over the past several weeks, we have been talking about aluminum and its alloys, and we have learned about different aspects of aluminum alloys, particularly with regard to the physical metallurgy. And we have learned about different concepts with regard to the physical metallurgy of aluminum, and we have also understood the structure property correlation. And with regard to that, we have also discussed different strengthening mechanisms for aluminum alloys, starting from work hardening to grain refinement. So all this we have discussed in past several classes. Now, if you remember, in the beginning I said this particular course has two components. One, of course, is the aluminum and its alloys, including the physical metallurgy, and that is what we have covered so far. So from today onwards, we are going to start the second part, that will be on the composite part, the aluminum based metal matrix composites. Okay, so this will be our topic from now on, and we are going to learn about the metal matrix composites, especially the aluminum based metal matrix composites, starting from their preparation to all the way to their properties and applications. Okay, so today we are going to start the aluminum based metal matrix composites. So if you remember, I had also mentioned in the beginning that this kind of composite materials are made with the objective of supplementing some of the properties of the monolithic metals. Okay, for example, if you talk about aluminum, it is a softer metal. The hardness is low, and therefore the wear resistance is also low for this kind of materials, right? So if you want to improve such properties, then you will have to take the help of a second phase which can have such properties and impart those properties in the metallic matrix that we are talking about. Okay, so for example, if you select a ceramic material as the second phase, then as you know, ceramic materials possess high hardness. Okay, and therefore if you could incorporate a ceramic material into the metallic matrix, then you can expect to improve the hardness of the metal. Okay, and that is how you can combine the properties of two different materials into one single material, and that is what is called as a composite material. Okay, so when you combine two or more materials together, which also gives rise to new set of properties that both the constituent materials cannot have individually, that's when we call that a composite. Okay, so if you want to define a composite, this is how it can be defined technically. The term composite broadly refers to a material system which is composed of a discrete phase known as reinforcement, distributed in a continuous phase that is known as the matrix, and which derives combination of properties not attainable by the constituents individually. Okay, so this is what I was mentioning, that it will combine the properties of two or more materials, and these combined properties cannot be achieved in the individual constituents of the composite. Okay, so that is the biggest advantage that you get out of composite materials. It can combine properties and supplement many of the properties which may be needed in a particular application. Okay, now depending on the matrix material, composites can be broadly categorized in three different categories: metal matrix composites, polymer matrix composites, and ceramic matrix composites. Okay, so our concern for this particular course will be on metal matrix composites, especially aluminium based metal matrix composite. Okay, so if you look at the different features or characteristics of metal matrix composites, these are the different characteristics of metal matrix composites, or MMCs in short. MMCs combine properties of metals such as ductility and toughness with those of ceramic such as high strength and stiffness and also high hardness. Okay, they possess high specific strength and modulus, low thermal expansion, and high wear resistance. And with regard to aluminium matrix composites, as you know, aluminium is a light metal, so you can expect a low density and also high specific properties. Okay, if the density is low, then the specific properties, that is any property normalized by the density, will be high. Okay, so for aluminium matrix composites, aluminium being a light metal, you can expect high specific properties such as high specific strength and high specific modulus. Okay, and apart from that, you also have good corrosion resistance in such materials, aluminium based composites, because aluminium itself exhibits good corrosion resistance. And the other advantage that you have for this kind of aluminium based composite materials is the abundance of aluminium. So therefore, availability of the raw material is not a concern for making such composite materials. Okay, so we are going to talk about all the details of aluminium based metal matrix composites, as I said in the beginning, starting from the processing of such materials and going all the way to their properties. Okay, so there are various methods available for processing metal matrix composites, including the aluminium based MMCs, and the processing routes can be divided into various categories depending on the state in which it is processed. Okay, such as liquid state processing, solid state processing, and vapor state processing. In liquid state processing, you have these methods: star casting, melt infiltration, and spray deposition. In solid state, you have powder metallurgy, diffusion bonding, and high energy, high rate process. And in vapor state, you have all those vapor deposition processes such as chemical vapor deposition or CVD, physical vapor deposition or PVD, and then you have electron beam PVD. Okay, so we are going to talk about all this one by one and see the details of these processes as to what are the raw materials and how it is done to come up with a metal matrix composite. We'll start with the liquid metallurgy route because this is one of the most commonly used, and it is also a simple method and at the same time economical. So we'll start with that and then we'll go into the other techniques also. So one of the simplest methods that you have in the liquid metallurgy route is this one, known as star casting. So as the name itself suggests, you basically start the melt and add the second phase reinforcement into the molten metal when it is being agitated. Okay. This is a schematic of the process. So the metal is melted inside a furnace, and once it is melted, then a mechanical impeller is dipped into the liquid metal, as you could see from here. So this is the impeller that you have, right? So these are the impeller blades, what you can see over here, right? And it is connected to a shaft which goes into a motor. So now if you rotate this shaft with the help of this electrical motor, then this impeller will be rotated inside the liquid metal. And as you rotate it at high speed, it will basically create a vortex in the liquid metal and will agitate the liquid metal. Okay, this is something that we have seen before while talking about the grain refinement by stirring and vibration. So this vortex which is created is actually helpful for incorporating the reinforcement What kind of reinforcement can be added? I will come to that in a moment. So let's say you are adding ceramic particles as the reinforcement. So this vortex which is created due to this stirring of the melt by this mechanical impeller will actually take these ceramic particles into the molten metal as you add the particles along the periphery of the vortex. Okay, so basically if you see, it will create some kind of vortex as you agitate the melt by a high speed rotation of the impeller. Okay, so you can physically see that this will create a vortex or a whirlpool kind of thing into the molten metal. So now if you slowly add the particles along this periphery of the vortex, then these particles will be sucked into the liquid metal because of that suction of the vortex. Okay, and then these particles will be dispersed into the liquid metal, and once they are dispersed uniformly, the metal is poured, and once it is solidified, then you will get a composite material. Okay, and for aluminium, sometime a gas cover is also used. An inert gas is used to prevent the oxidation of the metal. So that's what you see over here. A gas cover is used, and inert gas is used to prevent the oxidation. So it's a quite simple yet effective method of making metal matrix composites. And a variety of reinforcement can be added with the help of this star casting method, and a variety of metallic matrix can also be used. Okay, so if you see the matrix, these are the different metals which can be used for making composites by this star casting method: aluminium, magnesium, iron, copper. Okay, a variety of metals can be used. So our concern here is the aluminium, okay. And with regard to the reinforcement, you can see a variety of materials, primarily ceramics, are used for making the composites with the help of this star casting method. So this can be categorized as organic and inorganic. In organic category, you have red mud, fly ash, these kind of materials. These are basically some waste product out of industries like metal extraction and power plants. So if you have this kind of materials in the form of particles, they can be used as organic reinforcement in metal matrix composites. But the commonly used ones are these, the inorganic ones, and in this you have oxides, nitrides, carbides, borides, and some other materials also. The commonly used oxides for metal matrix composites are aluminium oxide, titanium oxide, silicon oxide, zirconium oxide, and sometimes zinc oxide also. On nitrides, you have titanium nitrides, boron nitrides, and silicon nitrides, and you have a variety of carbides which can be added. So all these materials that you see over here as the reinforcement possess two main properties. First, they are all hard materials, because one of the objectives of making metal matrix composite is to increase the hardness of the metal, and therefore the reinforcement has to be a hard material. And also these are strong materials, because we know ceramics are not only hard but also strong, okay. Oxides, carbide, nitrides, all of these possess these two fundamental properties that we look for in a metal matrix composite: the hardness and the strength. So these two properties are the main criteria for selecting the reinforcement. Apart from certain other criteria like the compatibility of the material with the metallic matrix, how well it can be bonded to the metal, and so on. Now let us look at some other methods also in the liquid metallurgy route. But before that, we can also have a look at the advantages and the disadvantages of this particular process called star casting. So first, let us look at the process parameters. A number of process parameters have to be controlled in this particular technique in order to get a quality composite material without defects. So the main process parameters are the temperature, both the melt temperature as well as the pouring temperature, the stirring speed, and also the dipping length of the impeller. At what depth the impeller has been inserted into the material, up to what depth it has been inserted, that is also going to have some effect on the vortex which is created by the rotation, okay. So apart from the stirring speed, the dipping length of the impeller will also have some effect on this star casting process. And then the impeller design itself will also affect the process in terms of how well the vortex can be created. So by changing the design of the impeller, you can actually modify the process in terms of the ease of creating the vortex or creating a better condition in the liquid metal for the incorporation of the ceramic particles, okay. And apart from that, the particle addition method also has to be considered, because how well the particles are added, that will decide how well they will be dispersed into the metal, okay. So these are the main process parameters. Mainly you will have to look at the temperature, the processing temperature, and the stirring speed of the impeller. So for every material you may have to optimize these parameters. So the advantage of this process is that it is a simple and a cost-effective method. In fact, this is one of the most economical method of making metal matrix composites on a large industrial scale. Okay, but the disadvantages are a number of parameters have to be controlled, as I said before, and if the particles are not added properly or if the process parameters are not controlled properly, then chances are that these particles will be rejected. Okay, because for these particles to be bonded, they will have to be weighted by the liquid metal, and if for some reason this weighting does not happen, then the particles will not be bonded to the metal and they will be simply rejected, and they will either float on the liquid metal or settle down at the bottom of the crucible. Okay, and apart from that, the clustering of the particle is also a problem in this particular technique. This again depends on how well you control the process parameters. So for uniform dispersion of particles or to prevent the clustering of the particles, the process has to be controlled carefully. And then, this gas porosity is also a problem because while creating this vortex, air bubbles can be trapped into the liquid metal because of this agitation of the melt, and that would lead to creation of gas porosity in the solidified composite material. Okay, but nevertheless, this is one of the most cost-effective and simplest methods of making metal matrix composites, including aluminum-based composite materials. So these are some of the impeller designs that you can see over here. As I was mentioning, the impeller design might also have some effect on the process. So these are different types of impeller design that you can see over here, such as a 3-blade propeller, 4-blade, 2-blade, or other kind of geometries. These would depend on what you want to do, what kind of material you have, and so on. So different types of impeller designs are available. So now let us see the other methods also in this liquid metallurgy route of making metal matrix composites. So in the liquid metallurgy route, we have another technique called melt infiltration. So in this process, the reinforcement is first assembled to make a porous preform. And once you make this preform, it is infiltrated by the liquid metal so that all the pores will be filled by the liquid metal, and as you solidify it, it will give rise to a solid composite. Okay, because now the metal will surround the reinforcement phase as it is solidified and give rise to a composite. Okay, and this infiltration can be done with or without pressure. So when it is done without pressure, it is basically the capillary force that is being utilized. So whenever a liquid comes in contact with the surface having pores, capillary develops, and that will actually take the liquid into the preform, into these pores, and the preform will be weighted by the liquid. So once the preform is weighted by the liquid, the capillary will develop and the liquid metal will go into the pores and fill the pores, and as you solidify it, it will give rise to the composite. Pressure can also be applied. For example, you can utilize hydraulic pressure to inject the liquid metal into the preform. And when you do this, such a process is also known as squeeze infiltration. Which indicates that the liquid is being squeezed or infiltrated into the preform by application of external pressure. But in any case, weighting of the solid by the liquid is crucial, and therefore the composition of the metal will play a role in this case, because how well the solid surface will be weighted by the liquid, that would depend on the composition of the liquid, okay, or the composition of the matrix material that we are using here, okay. So this has to be also considered when you make composites by the melt infiltration process. So let us quickly look at the advantages and the limitations of this process as well. Advantages are: it can produce near net shape products, with selective reinforcement, and composites with uniform microstructures can be obtained. The major limitation of this process is the fact that the reinforcement has to be assembled in a self-supporting structure. So this is a primary requirement. And there are chances of damage to the preform or fibers during infiltration. Which will lead to deterioration of the mechanical properties. So this was about the melt infiltration process.
And with that, we come to the end of this lecture. Thank you for your attention.